Hello class, this is Mr. Morgan, and we're going to talk about how distance, velocity, and time relate to each other in an equation. We've spent some time learning about each of those variables, and hopefully through a little bit of practice here, we're going to learn how to build those into your own equation that we're going to be using in physics class. So to build our first relationship, we're going to look at our dependent and independent variables. Of our three variables, distance, time, and velocity, which one is dependent on the other two? Do you know? Well, it's distance. Distance depends on how fast an object is moving, velocity, and how much time it moves at that velocity. To allow us to predict the distance an object has or will travel, we'll make an equation right now that will act like a moving object. In order to do this, we need to figure out what variables have relationships and whether they are linear or inverse. So let's look at those variables. The first set of variables that we're going to look at is distance and time as a relationship. So we're going to say that our velocity is a constant 1/2 kilometer per minute. And if we have an object that we graph its distance from the origin as a function of time, it might look like this. You've seen this line before. What can you say about this line? Is this a linear, inverse, or some other kind of relationship line? How can you tell? The other variable relationship for distance is velocity. If we wanted to see how much distance you could cover in a constant time interval of 3 seconds at a range of 3 different velocities, you could make the graph to the right. So velocity is increasing and our distance is also increasing. And remember, the time that we travel is constant. So if we travel for the same amount of time, but we travel at a higher velocity, we should cover more distance. Same concepts here apply as the previous slide. Is this a linear, inverse, or other kind of relationship? How do you know? So if we look at the graph, you should be able to tell that this is a linear relationship. So finally, we're going to take those two ideas that there is a linear relationship between distance and time and distance and velocity, and we're going to combine those two ideas to make our own equation about distance. Remember that once you've figured out all the variables in a relationship, you can derive an equation for anything. So we know our variables are distance, time, and velocity. So let's put them together. We know our dependent variable is going to be distance, so it's going to be on one side of the equation. And our independent variables are velocity and time. So we're going to put those on the other side of the equation. And we come up with the equation distance is equal to velocity multiplied by time. So now we have an equation, and let's try to test it out and see if it's ready to go. We have a scenario that we can try to plug our equation into and see if it gives us the right output. At exactly 12 noon, a football player was located on the 20-yard line. Can we find her velocity using this new equation? So think about it for a moment. We've got time, exactly 12, and we've got a location, 20-yard line. But is this enough to plug in and get the velocity? And hopefully if you thought about it for a moment, you realize that, well, the velocity can still sort of be anything under these parameters. We could be standing still, or walking backwards, or speeding up, or digging a hole. We could be moving up or down. We could be climbing a ladder. So we need to add some more to this equation before it's quite ready for physics. We need to add some mathematical operators. So let's look at the full equation as it works in physics. It's delta d, instead of just d, is equal to velocity average times change in time. Well, this is a little bit different. What does that mean? So why did we use delta D instead of just distance? Well, the reason is that we don't need to know an exact starting point or stopping point. We want to know how much the distance changed, right? How much motion was covered in order for our equation to work out. Why did we use velocity average? Well, usually during typical motions, velocities are going to change a lot over the interval of time that we're going to look at. And we don't need to know the highest or the lowest velocities. What we really just want to know is, over that amount of time, what was the average velocity if we added up all of its individual velocities together. Finally, we want change in time. So if I said we started at 12 noon, that wouldn't make much of a difference in calculating the distance. What we really need to know is how much time went by, and if we know that, and we multiply that by the average velocity, it'll tell us how much of a change in distance we should expect. And that's the equation as it works in order to show the relationship between these variables. So now that we've looked at the variables and their relationship, there's just a couple of points that I want you to remember before you go off and answer the essential question. A change in distance has a linear relationship with average velocity and with a change in time. What do you think that means about the relationship between average velocity and time, or average velocity and distance, right? So if we sort of jumble what's on the left-hand side of the equation, what might that change about it? Finally, pay close attention to the operators in the equation. Operators made a big difference in how those variables related to each other. Delta D is different value than D, and it's different value than D initial or D final. So those operators and subscripts make a difference. Your answers will come out strangely if you use the wrong variables or the wrong operators. So pay attention to those things. If you have questions, send me an email or write down your questions in the question section on your notes, and I'll see you in class.